Are you ready for this? Okay, I'm going to go through it step by step. We're going to walk through everything, every little detail in this integral, and it's going to make total sense. Now, the first thing to do is like, how do you start? And we can't do a u substitution here, right? Because there's no derivative of this denominator thing. So what I'm going to try is a trig substitution because I have two terms that are squares, and that's screaming trig substitution. So that's what we're going to do. And in that method, what I do is I take the square root, whatever it is, and I call it something. I'll just call it g. And I'm going to rearrange this equation such that it looks like the equation for a right triangle, a squared plus b squared equals c squared. So if I rearrange that, square it, we have x squared plus 4 equals g squared. And we're literally going to draw the triangle. I draw it every single time. G is in our hypotenuse, and then 2 and x, those are on the sides. Doesn't matter which side they're on. And I'll pick one to be the theta. I put theta here. It could be here, but here's our theta. Now, at this point, we want to write theta in terms of x. So we're going to use tangent using SOHCAHTOA. Tan is opposite over adjacent, so x over 2. So that's theta in terms of x. But we also need to sub in what g is, because g is in the denominator. So we want to know what theta is in terms of g. So we'll use cosine, because cosine is adjacent over hypotenuse. So that's 2 over g. Okay, now we want to know what dx is, right? So we need to solve for x and then take the derivative. And the derivative of tan is secant squared theta. It just is. I have a couple of videos showing that. You might just want to know it. Or you could use the power rule or the quotient rule or whatever. Anyways, it's secant theta squared. So there we are. Now, we want to know what g is. So g is 2 divided by cos theta. But I'm going to write this in terms of secant theta because dx is in terms of secant theta. So that makes everything in the same trig function. Now, at this point, we'll do our substitution. And our integral becomes dx, which is now 2 secant squared theta d theta. See that there? And then the denominator is g, but g is 2 times secant theta. And check this out. This is looking pretty nice, right? Our 2's cancel, one of our secant thetas cancel, and we're just left with the integral of secant theta d theta. So that's cool. Now, what did we do? Well, we went from an integral in terms of x to an integral in terms of theta, x to theta right here. And this integral, you might already know it, or maybe you have a table of integrals. I have videos showing that it's equal to ln secant theta tan theta plus c. You can see that. It's a little tricky to get there. There's a few different methods, but I'm going to show you step by step how to do this, how to tackle it a different way, and maybe more intuitive way, which I also have a video on. So we're going to turn it into cos. Sometimes if you don't know what to do, turn it into sines and coses. So our goal is to integrate 1 over cos theta. And if we're not sure what to do, try a u substitution. And you can try u equal to cos theta. It doesn't really work. I tried it. It kind of got more complicated. So I was like, hey, let's do u equal to sine theta and see what happens. So I did that. And then with u substitutions, we take the derivative. So du equals cos theta d theta. And we'll solve for d theta. D theta is du divided by cos theta. Do you see that? Divided by cos theta. So that's what d theta is in right here. And now we have like this cos squared theta in the denominator. And it looks like things got more complicated. We went from a cos in the denominator to a cos squared in the denominator. But we have a cos squared, and there's a 1 here. We can use this like simple trig identity, and everything's going to be a little bit better. So we'll use kind of the most famous one, sine squared plus cos squared equals 1. And cos squared equals 1 minus sine squared. But sine is u, right? So this is sine squared is u squared. So cos squared theta equals 1 minus u squared. You see that? So this, rather than 1 over cos squared, we now have 1 over 1 minus u squared. This is 1, move this over. Hope you see that. I hope that makes sense. Now, it looks like we traded one problem for another. But this 1 over 1 minus u squared, this is actually not too bad. We can do this using partial fractions because it's a difference of squares. Okay. You haven't seen partial fractions before. I'll go through it step by step, don't worry. But if you had, obviously this should look really familiar. What we're going to do is take this fraction and we're going to split it up into 2 smaller fractions. One has a denominator of 1 plus u, the other one has the denominator of 1 minus u. And we just need to know what these numerators are. And the reason we split this up is because like each of these fractions, we can integrate. That's just ln of the denominator. That's fine. We can do that, no problem. So we're almost there. But to do that, we need to know what the A is, and we need to know what the B is as well. But imagine we go the other way. Imagine we have these two fractions, and we want to go and make one big happy fraction, and we'll need to find a common denominator. So if we do that, we'll multiply this first fraction by 1 minus u, and then we'll multiply the right fraction by 1 plus u to get a common denominator. So then the numerator becomes a times 1 minus u, because we're multiplying top and bottom by 1 minus u, plus b times 1 plus u. And all of that has to equal 1, because when we merge these two fractions together, if we were to, it has to equal 1, because the numerator is 1, just with this du here, but this du is kind of coming along for the ride anyways. You see that? Now, we have one equation, and there's like 3 variables here, or 2 unknowns. A and B are unknown, and then a variable. I guess A and B are constants, but we shouldn't be able to solve it. But the trick is that because u is a variable, u could be anything we want. So we're going to conveniently, like sneakily, set it to be something so that we can solve for A and B. So first thing comes to mind is we'll set u equal to 1. And if we set u equal to 1, this left term cancels at 0. And then we have b times 2 equals 1, so b equals 1/2. Now you might be like screaming, hey, can't set u equal to 1 because we have 1 minus u in the denominator here. And if u is 1, then we're now undefined in this fraction. And that's kind of not allowed. That's true. We can't set u equal to 1 when it's in a denominator. But in this equation here, in the numerator, there's no restriction. We can set it equal to 1. That's not the problem in the numerator. It's only a problem if it's in the denominator. So we're okay. Okay, and now we'll set the other one. So we'll set u equal to -1 so that this term with b becomes 0. If we do that, then we have a times 1 minus -1. So that's a times 2. So a also equals 1/2. They both equal to the same value. That's not always the case, but in this case it is. So now we know what the a and the b are. We'll substitute that in. Now, rather than write 1/2 here, I just factored it out because it's a constant. It doesn't get involved in the integration. It's none of its business. So we pulled it out. And yeah, we got this. Now, at this point, we can integrate. And this is our friend. The ln integral of 1 over u is ln of u. We need to slap those absolute value signs because we can't have a negative number inside a log. So that's just kind of what we'll do. We have our 1/2 along for the ride, and then ln of 1 plus u, and then minus ln of 1 minus u. And we went from a plus to a minus because even though the integral of 1 over 1 minus u is ln of 1 minus u, there's a negative sign we need to account for. So imagine you have this ln of 1 minus u. Imagine you do the derivative. So the derivative should take us back to this integrand. But if we do the derivative, we get 1 over 1 minus u. We got to use the chain rule, take the derivative of the inside function, which is -1. The derivative of 1 minus u is -1. So there'd be a negative here. And we want it to be positive if we do the derivative. So that's why we have this minus sign to cancel out with the negative. Hope that makes sense. Okay, we got our integration constant. That's our friend there. And we did our integration, but we're not totally done because we're now in our variable is now u in terms of u. We started off with x, then we went to theta, then we went to u. So we got to substitute back. Now we could do this in one step, but I'm going to do it in 2 steps just so it's a lot more clear. And we need to know first we'll go back to theta. We set u equal to sine theta originally. So that's what we'll sub back. So u is sine theta, so that's not too bad. You might notice, I used a log law to merge these together. When you subtract logs, then you can kind of divide the arguments. That's just kind of a standard log law. Now we need to go back to x, right? And I don't know what x is I don't know what sine theta is for x because we set x equal to 2 tan theta. But here we have a sine theta. So when in this case, in something like this, just go back to the triangle that we had before. So we'll draw a right triangle. We'll use SOHCAHTOA. We'll put it in our g is in our hypotenuse, 2 and x. They got to be in the same spot as they were before. Now we want sine theta. Well, we're just going to use SOHCAHTOA. So sine theta is opposite over hypotenuse. So that's x over g. And that's literally what it is. So we'll substitute it in. And we're in terms of x, but we're also in terms of g. Got another problem that popped up. And your prof might not like this. Your prof might want everything totally in terms of g. So we can substitute back what g is. But before you do that, I'm just kind of like for like bonus marks, we're going to make this look a little bit more pretty because we have these compound fractions here. What we're going to do is we'll just simplify it a little bit. So we have this fraction. We have fractions inside of fractions. What we'll do is we'll find a common denominator. So like 1 is the same as g over g. So we can write this as g over g plus x over g, right? But we can make it as one fraction. And rather than g over g minus x over g, but then make it one fraction. And the reason we did that, check this out, yo. We have g in the denominator in both of these compound fractions. So those g's cancel. And we're left with g plus x divided by g minus x. So we kind of simplified our life, made it a little bit more prettier. We could plug that into there. So now we have g plus x divided by g minus x. And for all it's worth, we'll plug it back what g is in terms of x. G is the square root of 4 plus x squared. And there it is in all its glory. Our integration constant came along for the ride, and we did it every step of the way. If you walk through this whole thing with me, good on you. Pat yourself on your back. You nailed another one. On to the next integral.